Hello and welcome. We are Team 28 and this is our presentation on sleep stage classification. So why is sleep staging important? Sleep staging is important because it helps us diagnose various disorders and diseases such as Parkinson's and Alzheimer's. Sleep staging normally takes a lot of time and effort and hence is a very tedious task. So doing this automatically can help us save a lot of time, resources and money. So what are we trying to do in our project? We are trying to analyze the results of the traditional machine learning approaches and the deep learning approaches and see which performs better. We are evaluating the channels from the sleep EDF dataset to see which is more informative and which helps us classify data better. And we are evaluating the trade-off between training time and accuracy after performing dimensionality reduction using PCA. So these five are the traditional machine learning approaches we use. Logistic regression is a probabilistic model, and we wanted to see how it would perform on sleep data. We used multi-layer perceptron. We used random forest, which consists of multiple decision trees, and we thought this would perform the best. We used boosting, which combines multiple weak models together, and we used bagging with random forest and boosting together as a base classifier, and then created bags of data and performed bagging.
Next, we describe the architecture of CNN. The neural network architecture consists of two CNN networks. Small filter size is used to select the temporal information, and large filter size is used to select the frequency information from the dataset. Small filter size is of size 50 and larger one is of size 400. When CNN is combined with BiLSTM, the model looks like this. The BiLSTM model is deployed here to extract sleep transition features. The hidden dimension is 512 in either direction. We added a dropout layer of 0.5 to the output of each of the BiLSTM layers. The output of the 2CNN layer is now fed into a fully connected layer of 1024 hidden dimension, which is then combined with the output of the BiLSTM layers. Next is the description of experimental setup. We got our data from the sleep EDF dataset, which contains polysomnograms of 61 patients. This data compromises of two channels. The performance matrix used is accuracy and F1 score.
So these are traditional machine learning model results. We use a training testing split of 80 to 20%. As you can see, logistic regression performed pretty badly. Multi-layer perceptron performed the worst. Random forest boosting and bagging did pretty well with accuracy of about 53%. We performed bagging using Hadoop MapReduce. After PCA, the training time went down significantly while the accuracies fell. But in the case of boosting, accuracy fell just by 1% while the training time went down by 11,000 seconds. So in time critical situations, using boosting may be better, but otherwise random forest would be the best out of the traditional machine learning models.
Here are the stats for the CNN architecture. The accuracy for the best model is 80% with the total training time of 25 minutes. We were of the presumption that CNN will not perform well on the sleep data. This clearly suggests that the weightage of the local dependence in sleep data is much more than the large spatial dependencies. On the other hand, the accuracy of the CNN plus BiLSTM model on channel 1 is 82.9% with the total training time of 16 hours. However, the training time decreased considerably to 3 hours after the dimensionality of the feature was reduced using PCA. We also trained and tested the above model on channel 2 with an accuracy of 64.5%. This strongly suggests that channel 1 outperforms channel 2. We also observed that if we increase the number of data set and the feature set, the CNN model might perform as good as the combination of CNN and BiLSTM model.
As you can see here in the plot, deep learning models perform better than machine learning models. We achieved the highest accuracy of 82.9% with BiLSTM CNN model. Now we discuss the findings of our project. The dataset is very high dimensional and requires non-linear decision boundaries for accurate classification. Boosting and random forest perform the best amongst ML approaches. Our dimensionality reduction experiments speed up the computation manyfold while capturing almost 85% of variance in our dataset. This allows us to explore multiple approaches for classification. Now we can also see that deep learning is the best suited approach given the characteristics of our dataset. We have several ideas to improve the accuracy of our classifier. In the future, we would like to explore training the deep learning model on larger datasets such as mass and SSHR. We would also like to explore handcrafted expert-defined features as well as extend our models to use multiple channels for predicting sleep stages. Another idea we have is to do personalized sleep stage scoring with BiLSTM CNN model, where we would try to train and evaluate on each patient's data individually. While the drawbacks of this approach is that we have limited data available for any patient, our preliminary results show that this approach is also effective and worth exploring. Thank you.